All right. All right. So I will record this and post it on YouTube. I'll also put the kind of make a PDF of the notes. Do you guys think the notes are easier to follow after the fact, or the recording's easier to follow? Which have you used, if either?
Oh, for me, it doesn't really matter.
So you don't use either, is what I'm hearing. All right. Well, anyways, let me know if one of them is better than the other. Okay, so let's kind of um, let's kind of start here for today. Sorry, I'm trying to move stupid thing around. All right, so you guys should be able to see my it's OneNote, or no, sorry, Notability. That's what it's called, where it says pulling things together. Can you guys all see that?
Yeah.
Yeah. Okay, good. All right. So the goals this week is to pull things together. I've got some examples here to work through. I've got one little example, and then we're going to go through kind of like a flow of how to work through cycles. And so and there's going to be a lot of vocab, so make sure you know all the vocab as we go through it. And then I've got a cycle that we'll go through if we have time. Um, well, we'll get through it. All right. So the first thing is here's a little question. If you have an ideal gas, when is it? When can you have a polytropic process that is also adiabatic for an ideal gas? And this isn't maybe so useful as a practical example, but it's going to be incredibly useful when we get to um, um, ideal gases to Carnot cycles and ideal cycles. So when we get to entropy, this is going to be a really important thing so it's an important bit of algebra that I basically want to do now so that we don't have to waste time later doing it. All right, so let's unpack these. When you read ideal gas, what does that make you think? What does that make you think? What does ideal gas imply?
Temperature.
What about temperature?
So was it? You kind of neglect the pressure and things in ideal gas.
Yeah, so you're saying things like the internal energy, the enthalpy, well, yeah, basically that everything, yeah, and the enthalpy can all be written as functions of temperature, functions of temperature only, or at least approximately, if you're making this approximation. Yeah. Also, what else can we say about an ideal gas? PV equals RT for an ideal gas. So things are only functions of temperature, and we also have this relationship. All right, that's ideal gas. Let me even unpack this a little bit more. In particular, mostly we will assume for an ideal gas that the specific heats are constant, in which case we will say that the internal energy is CV times the temperature. These have to be absolute temperatures. And enthalpy is Cp times the temperature. And if you kind of go through the definitions of things, this means that R must be, is it Cp minus Cv or Cv minus Cp? Which should it be? Which one's bigger? Is the enthalpy going to be bigger or smaller than U? Think about the magician. Remember, enthalpy is the energy not just to have that bunny rabbit, but also to make room for it in the universe, which means that enthalpy is going to be bigger, least normally. It might be equal, but it won't be less than. So that means that R, because it's positive, should be Cp minus Cv. Okay? So this is what ideal gas law implies. Oh, somebody typed something. Sorry, I missed that. Okay. So Brian, does that logic make sense, what I was saying there? H should be larger than U typically because it also has the part of the energy. Okay. The other thing is there's a, I don't know what this ratio is called. There's people talk about a ratio of, and in engineering, people use this letter K for, which is Cp divided by Cv. And it should be greater than or equal to 1. I don't know. I don't know what the name of it is in engineering. In physics, we use the letter gamma for that in physics. So this is engineering, and this is physics. But in engineering, this is what is you like. I think that's one of the coefficients of performance, and so we won't use that symbol. We'll use K. All right. So this is just a ratio of things we've already seen. If you think about it, that means you can say that. Well, it says that Cp equals K times Cv. And it also means, using our formula up here, this tells me that I can write R is equal to K minus 1 times Cv. Oh, Cv. Just substituting in here and factoring out K minus 1. Or I can write Cv as R over K minus 1. So anyways, that's just some algebra, but it's going to be useful algebra. And that's why I'm doing it now, so that later on when we get to Carnot cycles and entropy, that this thing's going to pop out. And so, or we're going to need this fact. And so anyway, we're just doing it now to make things easier then. Similarly then, if I know Cv, I can multiply by K and get Cp. Okay, here's the deal. Every year when I teach this course, I memorize this or I learn it again. I can kind of do it off the top of my head, but I don't expect you just to be able to do that. I'm doing this so that later on, when we get something kind of similar to this, or we'll quickly do it later on, I want you to remember that there is some formula like this. Okay, that's really all I want you to do. The details, we'll go through it again if we need it. Is everybody clear on how I got this? Raise your hand if you understand. Specific heat ratio. All right, well, that's all right, Zach, that's a vacuous term. Yeah, right. But okay, yeah. No, I think there might be a more technical sounding term for it, but I just don't remember. I don't remember what it's called. I think it does have another name. Okay. All right, so that's ideal gas. That's what that means. All these things are things that might be useful. Hint, hint. Okay. What about adiabatic? Okay. What is an adiabat? What does that mean? Nobody remembers? Nobody? All right. Adiabat means the heat is 0. Adiabats have no heat transfer. Okay? So it's an adiabat. So right here, we're looking for an ideal gas, so all these facts, that has no heat transfer, so some process with no heat transfer, and we also want it to be polytropic. What does polytropic mean? Billy, what does that mean?
It's where it comes back to where it started, isn't it?
No, that's a cycle. Polytropic means P times V to the N is a constant. Okay, that's polytropic, right? Okay. Now, if it's polytropic, we worked out the formula for the work. The work, or the specific amount of work, was 1 over 1 minus N times P2 V2 minus P1 V1. If N wasn't equal to 1, or the other case was P1 V1 log V2 or V1 for N equals 1. Okay? Raise your hand if you remember these formulas for polytropic. Gabe, Billy there, yeah. Michael's on. Sydney, you okay? Oh, sorry. Oh, Brian, you had it. I'm sorry, Brian. I keep missing the chat. It's because I don't have enough screen space, so I have to keep it small. Yes, you're right. Okay, so now basically we want to know under what condition are all of these things simultaneously true. So, well, let's go through. If Q is 0, then the first law of thermodynamics says that delta U equals minus the work. But for an ideal gas, delta U, well, we go back up here and we see, oh, U is CV times T. So delta U is going to be CV times delta T. On the other hand, the work, we'll just assume it's a general polytropic process, and then, worst case scenario, we just resolve it for any, if it happens to be 1, but it won't be. It's 1 over 1 minus N times P2 V2 minus P1 V1. Is everybody clear how I'm where I'm getting these formulas? Give me a thumbs up if you are. All right. Okay. Now, remember, it's an ideal gas. So I'm going to circle this for no particular reason. Anybody have any thoughts as to what might be a better way to rewrite this right-hand side for an ideal gas?
R times the change in T.
Yeah. So you're going to rewrite these terms as RT, RT2 and RT1. Use the fact that it's an ideal gas. So we get CV delta T equals 1 over 1 minus N. Well, you can factor a common factor of R. You get T2 minus T1. Or just trivially rewriting this, CV delta T equals, oh, sorry, I missed the minus sign. That should have been there. So I put a minus sign there. And then I'm going to make this minus sign go away. I'm going to flip the denominator around. I just use that minus sign to change the order. Okay. Does that look at all familiar to something we've seen like 5 minutes ago? Oh, okay. Sydney, just saw your message. Let's go back up. For an ideal gas, we have a formula for CV. It was R over K minus 1, where K was the compressibility ratio. But for a polytropic process to be, okay, so let me use that. So this what says that R over K minus 1 times delta T equals R over N, whoa, N minus 1 times delta T. And what do we learn? When is Q equal to 0? What kind of polytropic process do we have to have? When can this be satisfied? N has to equal K. Okay? Raise your hand if you we'll take a second and maybe run through the algebra a little bit, but raise your hand if you see where this result's coming from. All right. So what this means is that for an ideal gas, if you plot in a PV diagram, an isotherm, whoa, sorry. These are isotherms. For an adiabat, so remember, for an ideal gas, K is bigger than 1, right? Because CP is bigger than CV. Therefore, for an adiabat, if you're going to sketch it in for an ideal gas, then for an adiabat, something with no heat, it has to say you start here and you're on an adiabat, it has to fall off faster than 1 over V. So it has to be something like this. So this has got Q equals 0, whereas this is T is a constant. Or isothermal. So adiabats fall off kind of more steeply for an ideal gas. And that's typically kind of what they look like, at least if it's a vapor or gas, than the isothermal curves. Okay? Does everybody see? Do you understand the logic of how I kind of sketched that in? Now's the time to ask if you don't. What's going to happen is here in a few weeks, we're going to start talking about cycles, and we're going to try to work out what's the best possible cycle, the one with the least possible heat loss. Namely, whenever we can, we're going to make it adiabatic, and we're going to run it using an ideal gas just so we can do the math. And so we're going to need curves like this to kind of draw out the best possible cycle, most efficient possible cycle. So this is useful algebra that we're going to have later on. Okay. So if there aren't any questions, then let's go on to the next thing. So what I have next is just like a general, I don't know, guide here to analyzing cycles. So remember, a cycle is a closed loop in a phase diagram. So a cycle, if you draw P, V, and you have states 1, to 3. You could have other ones. You go from 1 to 2, 2 to 3, 3 back to 1. Okay, for analyzing a cycle. So the first thing is to identify or to determine uniquely each state. You must know at least 2 different properties, always 2. And if you can't find those two different properties, you won't be able to solve the problem. So that's the first thing you need to do. Check that you have a way to get 2 numbers for each state. So check this first. Don't waste time trying to worry about other things until you've done this. You don't have to get the numbers, but at least mentally verify that there is a way to do it. You might then you might have to go and do the algebra to find it, but that's the thing. All right. Then each state is going to be connected via some sort of a process. The ones that we have that come up a lot and we give names to are the following. So you must know what each of these words mean, because otherwise you're just screwed. That's the technical term, right? You must know what the words mean, or you can't figure out how to go through a problem. All right. So let's go through these. Somebody, I don't care who, call out. What does isobaric mean?
Constant pressure.
P equals constant. Good. Somebody else, what does isochoric mean?
Volume's constant.
Isothermal, what does that mean? Somebody else.
Constant temperature.
Good. Adiabatic, what does that mean? Brian? He already typed it. Q equals 0, no heat. No heat. Polytropic, what does that mean? Polytropic means P times V to the N equals constant. Okay, these aren't the only processes. There are more, but these are the only ones where you can kind of do simple math to get the answer. The rest of the time, you're going to have to be given something, or you have to be given a lot more information to solve it. Okay, these are the ones which come up a lot in textbook problems. They may or may not be realistic depending upon your system. Okay, now you have to know these things. Then when we're trying to evaluate things like the efficiency or coefficient of performance, the goal is usually, I mean, who cares about the amount of internal energy or the amount of enthalpy change? Nobody cares about that. What we care about is the amount of heat and work. So we're going to go through, how do you determine work? And then over down here, we're going to find, how do you determine heat? Okay. How do you determine the work if it is isobaric? What do you do? Remember, the general definition for work is the integral of P dV. That's the general definition. So I guess that should go down here with other. Just use the general definition. Okay, that's kind of the other. If pressure is constant, you can pull pressure out of the integral, and this becomes P delta V. All right. If it's polytropic, then you get 1 over 1 minus N times P2 V2 minus P1 V1, or if n equals 1, P1 V1 log V2 over V1. Okay, if it's isochoric, what is the work? Can someone just shout it out?
0.
It's big fat 0, because there's no change in volume and the integral gives 0. Awesome. The other situations, either you have to use the definition of work or use the first law and say that the work is Q minus delta. Whoa, what was that? Delta U. Okay, so you either use the defining equation for work or use the first law, and that's it. Okay, this is an important page here. So before I go on, ask me now if there are any words you're not clear of, or any of these facts which are not just something you know off the top of your head. Nobody? No questions. All right.
The ln of V2 over V1 is just what we get when we move things around, right?
Yeah, you just, if it's polytropic with n equal to 1,
Okay.
then that's what you get. And notice if n is equal to 1, then P1 V1 equals P2 V2. It's a constant, which means you could write this as P2 V2 log V2 over V1, because they're just equal in that case.
Would that second one be V1 over V2 then?
No, it always, because the integral is from initial to final. That part's the same.
Okay.
It's just, this is the constant that sits out front. Any other questions on that? All right. Okay. What about ways to find heat? Heat is trickier because we don't see it so much. So in many problems, you're just told that you have a boiler that dumps this much heat, or you have a heating coil or something that does that. But okay, how can you calculate heat when it's not just given to you? Well, the first way is if you have a specific heat. So what is the definition of a specific heat in general? Well, in general, specific heat is not a property, and it equals del Q over the partial with respect to temperature. That's the definition. It's a partial derivative. Special cases are if pressure is constant or volume is constant, then you can write it as Cp and Cv. But in general, this is what you have. Because this is a partial derivative, you cannot just integrate this, right? You can only if it's a total derivative can you integrate it. However, if things mostly depend on temperature. So I'm saying that things don't change very much with volume or pressure or that kind of stuff. Then you can write this as Q, well, you just do an integral of C, and it could be a function of temperature, dt. So basically I'm saying if this partial derivative is pretty much a total derivative, then you can integrate it. All right. Is everybody clear on why you cannot always integrate it? Think about, well, so that's a Calc 3 kind of question. when the difference between total derivatives and partial derivatives. All right. Now, if, which is most of the time that we care about, the specific heat is constant, you can pull it out of the integral and you can say the heat is C times the change in temperature. Okay, and that's just saying if the specific heat is constant, you can pull it out of the integral. And we did that in an example in class last week where we, you had water and hot and cold water, and we just said that the heat was C delta T, or the total amount of heat was MC delta T. That's what you do in chemistry class. You use this formula.
From your calendar.
All right.
Science Everson starts in 2 minutes.
Hold on one second. All right. Is everybody okay with this? So the specific heats are one way you can go about finding heat. What if a process is isobaric? How would you find the heat then? If a process is isobaric, how do you determine the heat in that situation? No. Okay. If it's isobaric, then we learn that Q is equal to the change in enthalpy. Only if it's isobaric. All right. Only if it's isobaric can you write Q is equal to change in enthalpy. And also, if you think about this, and you go back up here to the work formula, or work part, if it's isobaric, that means that you can also say that the isobaric work is, so work is equal to Q minus delta U, which is the same as saying delta H minus delta U. Sorry. If it's isobaric. So the work can be related to changes in enthalpy and changes in internal energy if it's isobaric. Right? And then the other one is if it's adiabatic, the heat is 0. And other than that, we will have some other ways to do this, but basically hope or use the first law. Delta U plus the work. Okay, there's going to be another way to write this in terms of entropy, but we don't know about that yet, so I don't have another way. But basically, hope is your best guess at that point. You have to, or come up with some other way, but usually it means use the first law. All right, so this is kind of our guide, our roadmap to solving these problems. There's a question. What was that last formula? Which one, Brian? Those two.
I think it was the ones you squared in right there under isobaric.
Oh, so, okay, so on this one, if it's isobaric, remember, so if it's isobaric, the heat is delta H. On the other hand, so if it's isobaric, I can write the work, well, it's always Q minus delta U from the first law, but if it's isobaric, Q is equal to delta H. So I can go back and say that the work for isobaric processes is delta H minus delta U. Excuse me. Sometimes that's useful, sometimes it's not. Does that make sense, Brian? Okay. I'm just combining a couple little things that we've had. I'm sorry. So, are there questions on this? This is your roadmap for solving problems right here. Being able to go through all of these, and you have to know what each one of these words mean because they're going to come up. All right. We have 20 minutes. All right. What we're going to do is we're going to plan our way through this problem. I don't know that we will get the numbers out. So we're going to plan our way through this problem, and the next class we'll go through it in detail. All right. Okay. So here's the following system. It's got refrigerant 22, and somebody didn't have refrigerant 22 in their book. Was that you, Brian? I can't remember. Anyways, it doesn't matter. I will, you have to, anyways, don't worry about it. I made a scan of it. So when we get time, when we go to look up numbers, I will put the tables in there. So don't worry about that. Okay. So there's a system of refrigerant 22. I think that's the one that's not legal anymore. And we have 1 pound of it, and it undergoes a cycle with 3 states. Now, it just tells me it's a cycle, but since it's refrigerant 22, probably, if I'm making a guess, I would guess it's going to be a refrigeration cycle, but we'll see. All right. From 1 to 2, they tell me the pressure is constant, and they tell me P1 is 30 psi, X1 equals 0.95. What is X1? Can somebody call it out?
Is it quality?
It's quality. So the quality at state 1 is 0.95. So when you read that, what should you be thinking about state 1? Where do you know anything? Where, like, can you imagine? Can you picture where it might be in a phase diagram?
Very close to gas.
Very close to the saturated vapor side, yeah. But it's inside. It's in the mixed state. Yep. So these are the little things. When I read this, this is what's going on in my mind. And then state 2 is 40 degrees Fahrenheit. Do I know anything else about state 2? It's 40 degrees Fahrenheit. So hold on, I'm going to make a little table here. State 1, I know P1 is 30 psi, and I know quality 1 is 0.95. So I have 2 properties that I know for state 1. Okay. What about state 2? What do I know about state 2? Well, they tell me it's 40 degrees. Do I know anything else about state 2? Can somebody call it out?
It's 30 psi pressure.
Yeah, because it's an isobaric process. So I also know P2 equals P1 equals 30 psi. 2 things. 1, 2. All right. If I can't figure out 2 facts about each thing, or at least kind of see that in the problem somehow 2 things can be assumed, then I can't proceed. So I've got to make sure that I've even got a chance to get that. State 3. Okay, so from 2 to 3, I have a constant temperature to saturated vapor. So, okay, temperature is constant. Sorry. All right, so at state 3, so from 2 to 3, the temperature is constant. That means temperature at state 3 is the same as temperature at state 2, which is 40 Fahrenheit. So that's one thing. What else do I know about state 3?
The work.
I know the work, but the work is not a property. So that'll be useful, but it's not a property, not yet. I need a pro- What was that? Go ahead, sorry.
It's a saturated vapor.
Saturated vapor, which is the same as knowing quality is 1. Okay, so I know sat vapor, or I'll just write it that way. I know that the quality at state 3 is 1. Okay, so at each state, I have 2 facts that are properties, not okay. The work is kind of is about the process, not about the actual states. All right. Excuse me. All right. Great. So now let's go through. What do they want me to find? Sketch the cycle in both diagrams, PV, TV, neglect kinetic potential energy. Yeah, because basically we always do. Determine the net amount of work for the cycle and the heat transfer for each process, all in BTUs. Okay, so we want to know, we want Q's and W's. Actually, no, let's be more careful. They say the heat transfer in BTUs, so we want capital Q's and capital W's. Okay, so if you find lowercase q, you have to multiply by 1 pound, so to get to the capitals. All right, that's the kind of stuff we want, and the graphs. Okay, take a second. We have a few minutes left here. We have 13 minutes left. Take a second and try to sketch your diagram. I'll give you guys 5 minutes to do your diagram, and then I will go through the diagram. And then what we're going to do is we're going to go through the diagram, and then we will come up with a list of numbers to pull out of the tables. And then we'll probably stop there. Okay, you have enough that you can sketch the diagram from this. Is there anyone who's stuck making a table at all? If you're stuck, let me know so I can try to fill in details. Okay. If you're done, raise your hand. Okay. Raise your hand if you're making progress. Some people. Josh, are you doing okay? Josh, you doing okay? Alex, you doing okay? Alex went to go have lunch. One more minute and then I'll kind of start. Okay. So the first thing I do is I sketch in the phase diagram, the phase transition, the mixed state region, saturation curve. There you go. Sorry, looking for the word. Okay. And then I'm just going to kind of go through from state one, try to use that information to sketch it, and then go from there to the state two and so on. So state one, I know it's 30 psi, and I know the quality is 0.95. So for state one, I know that it's at 30 psi and state 0.95. So it's close to the saturated vapor curve. It's a little farther over than that, but I don't have much room. So I'm going to say that's 30 psi. That's where I'll put it on a pressure diagram. And I know that's going to correspond to some temperature. I don't know the number yet, but it's going to be the same way. It's going to be just inside the saturation curve here on the temperature diagram. So that's going to be state one. All right. Now, state two, so from 1 to 2 was constant pressure. And I know that state two is at 40 degrees Fahrenheit. So I know that state two is on the pressure diagram. I know that state two is at constant pressure. So it's got to be along a horizontal line. And what I know about this TV diagram is that once you get out, and I know that it's going to be a mixed state just because now they're giving me pressure and temperature. Those are only independent pieces of information if you're in the vapor region. So it's going to be over here to the right, and I know that when it behaves like a vapor, generally it sort of is like an ideal gas. And so therefore I know that as the temperature goes from 30 to 40, and I know the pressure is constant, it's going to be kind of up along sort of a more or less a linear curve. So it's going to be up here. So state two is going to be up here because I'm basically following an isobar on an ideal gas. Even though it's not an ideal gas, it roughly moves in that same direction. So state two is going to be up like that. And so from 1 to 2, I'll connect it with a blue line. From 1 to 2. Sorry, that last one's wrong. When it's in the mixed state, the pressure is constant. So in the mixed state, it goes over horizontally and then up. Kind of has a kink in it from 1 to 2. All right. Now, what about state 3? For state 3, I know that from 2 to 3, the temperature is constant and it finishes at saturated vapor. So that tells me that state 3 has to be along a horizontal curve in this diagram and finish at saturated vapor. And over here, I know the temperature is constant, and I know that an isotherm in a PV diagram, it has a bend to it, but it basically, and I know it's going to finish here like that at state 3. It's saturated. It's because it's saturated. And I know roughly, qualitatively, the shape of an isotherm in a PV diagram. Okay, so I know that here it's going to be horizontal. And I know here it's going to have like a bend to it, but I can't really draw that very well. So that's what it's going to look like. And then from 3 to 1, it's an adiabatic expansion. Well, I don't have the thing we did before about an adiabatic, the shape of an adiabat, that was really just for an ideal gas. But here we are deep in the middle of the mixed state. So it's kind of hard to sketch something, but I just expected to just connect these up like that. Back to 1. Okay. Raise your hand if your diagrams, hold on here, let me get the thing up. If your diagrams look anything like my diagrams. Raise your hand. Do your diagrams look like my diagrams? Gabe says yes. Okay, so other people aren't saying that theirs look like mine. So how are yours different? Somebody, what was it that you had backwards? They do now, Brian says. Okay. All right, fair enough. It's okay. Like reading these, or figuring out these diagrams, it's a skill, right? So what was the thing that, what threw it off? How many people were able to raise your hand if you were able to figure out where state 1 was? Roughly. I mean, at least qualitatively. Alex says, Michael says. Okay. All right. Josh, were you able to figure out state 1? He was. Okay. And what about Billy was? Okay, good. All right. State 2. Were you able to figure out state 2? Okay, it looks like state 2 is the one that got people. All right. So the way I do it is, well, first of all, in the PV diagram, that was easy because it's an isobaric horizontal line. In the TV diagram, I just, I think to myself, well, all right, up here in the vapor state, I know that for an ideal gas, PV equals, RT. So if pressure is constant, that basically RT, there's a line between them. It just grows linearly. It's positive slope. So it's like that. Now, right, so I mean, we're not really doing this all to scale. So the slope doesn't really matter, just that it's a roughly linear out here at constant pressure. So I'm using the ideal gas law in the back of my head to help me sketch this, even if it's not exactly right. It's ballpark. Give me a thumbs up if you kind of understand my logic there and how I kind of do that. All right. Gabe, does that make you okay? Sapan? All right. Then TV means I just come back to a saturation curve. So it's got to be, it ends up, it has to be higher up than it started. So it's up here. And so that just tells me immediately, and if it's higher up on the saturation curve than it started in TV, it's going to still be true in the PV diagram because they qualitatively are the same. So it ends up here, higher up. And again, I'm using my intuition from an ideal gas when it's in the vapor state to roughly let me say that if it's isothermal, if temperature is constant, because that was right from, yeah, constant temperature. So it's roughly got to be kind of like like a ideal gas kind of process, even though it's not really. It's roughly right. And then I just close it off as needed. Okay. Good. All right, tell you what we're going to do. So on Wednesday, so you got homework for Friday. On Wednesday, I will post, oh, son of a, I will post this PDF to Blackboard. What I want you to do was for Wednesday, you don't have to solve it, but I want you to try to come up with a list of numbers that we should be pulling out of the book from the tables. And then I have a list written down too. And then we will check that our lists are the same. And then we'll work through it and solve the problem. Okay. So is everybody clear what your homework is? Okay. So what I will want you to do is to, I don't know, chat, type in what the list of numbers that you think we should pull out of the tables and to solve the problem. It will be useful to go back and look at what kind of numbers you need to evaluate work and heat. Okay, that's why we went through that. All right, so you can use that road map or that guide page to kind of identify what are the numbers that we should pull out to solve the problem. Okay, so that's that. Also, as a reminder, apparently we're coming up on evaluation time of the year. So almost Thanksgiving, I guess. So I guess the way we're doing evaluations in Blackboard is there is a link in Blackboard. It doesn't go to me, so I don't think I know quite what goose eggs. Just if you can go through in Blackboard, I don't know if it's in, I think it must be in the course page. I don't know. I don't see it. So I don't quite know what you guys will see, but I think it's under the course link for Thermo. You should see some sort of evaluation link. So if you could go ahead and fill that out. It's always good to have feedback this year, especially because it's my first kind of full semester doing this online. So so if you can give me thoughtful comments, that's better than just, your jokes are hilarious. I mean, I know that's tempting for you guys to write that every single one, that I have the best jokes ever and all that. But anyways, all right. So I'll let you guys go. If you can fill that out, I'd appreciate it. We have till the end of the week, but if you could remember to do it earlier, it's better. And the next class, I want to know what are the numbers you're going to pull out of the table, and then we'll do it. All right.
Hey, Sean.
Yeah.
I had a question about the strength of materials class. I don't know if you saw my email.
I saw you had sent something, but I didn't have a chance to.
I mean,
hold on, let me stop.
They're basically the same class.